All right, I'm happy to introduce our very own Lei Xue, giving a talk on a proof of Grünbaum's lower bound conjecture on general polytopes.
Thank you, Kevin. Thank you for introducing me, doing my usual job. I am indeed going to talk about a lower bound conjecture by Grünbaum on general polytopes and the proof of it in the main seminar. And then for the pre-seminar, I'm just going to try to define the definitions in a relatively slow pace, like define whatever I need for the main talk and try to give you still some structure of it or intuition behind them. Feel free to ask any question or just let me know if my string gets frozen. Let's go. So the first part of the pre-seminar will be a crash class, Polytope 101, starting from the definition of a polytope. So if you take a finite set of points in Rd, for example, think of the space R3, and you take the convex hull of them, that will give you a polytope. And if you further ask that set of finite many points to be affinely independent, then you get something called a simplex. Here are two examples. The green one, both of them are polytopes. The blue one is a three-dimensional simplex. And we can further define faces of a polytope. So given a supporting hyperplane, that is a hyperplane that barely touches the polytope, so they intersect but only on the boundary, nothing in the interior. And if you take a look at the intersection, that will be a face. And here, this is a two-dimensional face. And here's another supporting hyperplane that touches the simplex only at a point. That'll make that point a face too, and it's a zero-dimensional face. So a k-dimensional face is called a k-face. And depending on the dimension, we give them different names. So zero faces points are called vertices, and then one-dimensional faces are edges, etc. And for d-dimensional polytope, there's a unique d-dimensional face, which is itself. And we call those maximal proper faces of a d polytope, those d-1 dimensional ones, facets. And we have this nice vector called face vector or f vector that can help us keep records of the number of faces of each dimension. Okay, here's another example, or the same example. I've just said, so dimension 3 is the highest dimension I can draw. So all the examples you see today will be as nice as this one. Okay, so here's a three-dimensional polytope with 10 vertices, 15 edges, and 7 two-dimensional faces. That's why it has this face vector on the left-hand side. Okay. And for the pre-seminar, we're gonna zoom in and look at a subset of polytopes, a special family of polytopes called simplicial ones. And they're defined as polytopes whose every facet is a simplex. In 3 dimension, think of polyhedrons with like faces that are only triangles. And for this special family of polytopes, there's one of the most important results for this family is the following. Lower bound theorem proven by Bartlett in 1973 and Cowley for the equality case in 1987, which says that basically if you fix a dimension of such polytopes to D and the number of vertices to N, then something called stacked polytopes will have component-wise minimal F vector. We're going to define stacked polytopes in a minute, but I first want to explain component-wise minimal F vector. It basically says that these polytopes will have minimal number of I faces for each I, okay, among the family of all simplicial polytopes. And we denote a stacked polytope P n comma d, and here's how we define them. It's a recursive definition, so if you only have d, this doesn't look right, so this is p3 comma 2 because we have 3 vertices. I better correct that. Okay, that probably will make yeah, so if n equals d plus 1, a simplex is a stacked polytope. And then we can do a stacking operation. Okay, this is 3, and here we have 4 vertices, so this should be 4. A stacking, you can think of it as gluing 2 simplex at a facet. Okay, so here we're gluing the blue one and the green one at that facet, which is an edge. So this will result in a simplicial polytope with 1 more vertex. And you can keep doing that. So I think the first component of this P and D things all got wrong. So this, yeah, so this really should be right? This one has 5 vertices, and you can keep doing it. And all of these are stacked polytopes. Here are some examples of dimension 1 higher. So if you start from a 3-dimensional simplex, you can stack over this yellow facet. Yeah, it's a little bit yellow, to get P5, 3. And then you stack over this pink one to get P6, 3. And we can count the number of faces of such a polytope. So if you stack from Pn minus 1, d to get Pn, d, then you're losing a d minus 1 dimensional simplex, but you're adding a d dimensional simplex, right? So you're adding d plus 1 choose I plus 1, but then you also need to subtract d choose I. Does that make sense? Okay, so that's how we get this general formula for the number of faces for stacked polytopes. And yeah, and they will together form the component-wise minimal F vector. Okay, and in the main talk, we're going to focus on not simplicial polytopes, but just polytopes in general that we defined before. And we're going to go over a construction by Grünbaum in his book in 1967. And yeah, and we're actually going to go over that construction here now. Let me just first give the definition needed for such construction, step by step. So the first one is a pyramid. If you start from a d minus 1 dimensional polytope and you add a new vertex, which increases the dimension by 1. So you add a new vertex that's not in the FN span of this P. Then you get a d-dimensional polytope. So the original one is called, the d minus 1 dimensional polytope is called a basis. And the vertex you added is called an apex. And you can keep doing this. If you're doing this, and each time you're increasing the dimension by 1. So if you do it k times, that's building a k-fold pyramid over your basis. You can also do something called a bipyramid. There are more than one ways to define it, but I will think of it as having 2 identical pyramids over the same basis, and then you glue on the basis. Okay, so yeah, just one confusion is between bipyramid and 2-fold pyramid. They're different. So bipyramid, it's similar to pyramid. It only increases dimension by 1. Okay. And then we also need to define this. So given a polytope and a point X that's probably outside of it, out there in the space.
Sorry.
Yeah, question?
Can you, so a k-fold pyramid, does it, so that involves attaching k new apexes.
Yes.
Do they have any link between each other, or?
No, each of them will be in a new dimension.
Yeah, I mean, like, so like we consider the, okay, yeah, okay, I get it. Sure, convex hull, yeah.
Okay, good. Yeah, okay, so I guess we can go on. Yeah, so we want to define what it means by saying a point outside of a polytope is beyond a facet. We pick a facet, call it F, and here, it's intuitive, right? This X is floating above that table, so it's beyond that facet F in English, but rigorously, we say X is beyond the facet if you look at the supporting hyperplane of that facet, and it should have the entire polytope on one side and that point X itself on the other side. Okay. And once we define this, we can, given an X, we can ask how many facets is that X beyond. So here in this two-dimensional example, this yellow point is beyond exactly one facet, this one, because, right, this supporting hyperplane will separate the point from the polytope. But for example, if you look at this one, it's beyond two facets. This one, and then that one, nothing more. Okay. And now I think we're ready. No, okay, I lied. There's one more definition called dual polytope. This is a relatively hard one. It's denoted as P star, called P dual. So given a polytope P, its dual polytope is a polytope of the same dimension. It's also d-dimensional. And the face pole set of the dual polytope will be the flip over, upside down, of the face pole set of the original one. In other words, let me first give this pair of examples. So these two polytopes will be dual of each other. So the dual, the facets of the dual pole set will be corresponding to the vertices of the original one, and vice versa. So in other words, I'm claiming that this facet, this rectangle facet of this green polytope will be corresponding to this vertex of the purple one. You can see that this, so in the green polytope, this rectangle contains 4 vertices, and that's corresponding to this vertex in this purple polytope that's contained in 4 facets, like it's flipped over. And so I spent like 10 minutes yesterday to actually draw this face pole sets out explicitly. So this rectangle is corresponding to this vertex, this element in this pole set. And this, oops, let me go back. And this vertex is corresponding to this element in this pole set. And you can see that they're sort of flipped over. Okay. Yeah, now we can start Grünbaum's construction. We start from a simplex of some dimension A, and denoted as T superscript A. And we put a new vertex that's beyond exactly m number of facets of that simplex. That will give us a polytope of still the dimension A, and it's still gonna be simplicial. And we call that, Grünbaum called that polytope TA sub m. And then we just take multifold pyramid until we reach dimension D. So this polytope that we end up with, it has, 3 indices. So on top, the first index D denotes the dimension, and the second number, D minus A, denotes the number of times you're taking pyramids. Okay, here's an example. So we start from a 2 simplex, which is a triangle. And if we want to arrive at T2 sub 1, then we're adding this new vertex beyond exactly 1 facet of this triangle. So how about here, right? It's beyond exactly 1 facet, which is this. And we take the new convex call. This is T2, 1. And then to get T3, 1 sub 1, you just need to take 1 fold pyramid, just cone over it. And this is what we get. There's actually one more step where we take dual of this polytope, but I run out of space, and you can try to see that coincidentally, the dual of this polytope, T3, 1 sub 1, is itself. So yeah, okay. Okay, so we were going to talk more about that family of polytopes that we just generated. And we're going to see probably those definitions again in the main seminar. But for the last part of the pre-seminar, I want to switch gear and talk about something that's not polytope. A generalization of polytopes, and they're called strongly regular CW spheres. Okay, I have 13 minutes. I think that'll be enough. Yeah, it has many terms, and I'm going to define them term by term. So first of all, the set of all strongly regular CW spheres contains the set of all polytopes. And actually that set, the set on the right-hand side, is usually a lot bigger. We're going to start by defining CW spheres. So CW spheres are CW complexes that are homeomorphic to spheres, or you can think of them of the shape of spheres. So, and for CW complexes, I'm going to give the rough definition inductively. So in 0 dimension, CW complexes are nothing but points, set of points. And whenever you're given a d-1 dimensional CW complex, you use that as your skeleton, or sort of like a frame. So you have that frame ready there. And then you can get a set of d-dimensional balls. And then we attach those balls to the frame or to the skeleton by gluing on the boundary of those balls. Okay, here's a friendly example. So there's a line segment here, which is a 1-dimensional ball. And the frame I have here is just 1 point. It's a 0-dimensional CW complex. I'm gonna glue that one ball to this orange vertex by gluing on the boundary. So then I get a circle, right? So and a circle is a 1-dimensional sphere. So this is a 1-dimensional CW sphere. And with this 1-dimensional frame or skeleton, what if I want to build a 2-dimensional one? I have these two balls, the blue one and the green one. You couldn't tell, yeah, hopefully you can tell the difference. Ready, and I'm gonna glue them to this circle on the boundary. And this is how I do it. Then I get a 2-dimensional sphere. Okay, and it has the shape of a sphere, so this is an example of a 2-CW sphere. Again, this is a relatively rough definition, but hopefully you feel good about it.
Where does the CW part come in? This just seems like a normal sphere to me.
Okay, so first of all, this is not regular. I mean, regular has its meaning here.
Sorry, I was trying not to use the word regular. I meant this just looks like a conventional sphere to me.
Yeah, because I'm only given the nice examples here. I mean, if there are many CW complexes that are not in the shape of sphere, is that right? Like weird shaped ones?
I don't know.
Yeah, okay, unfortunately, I do not plan to give the extended rigorous definition of the CW complexes, but I do have a nice reference. I think if you look at Hatcher's book, Algebraic Topology, I think it's in chapter 0, where it gives a rigorous definition of the CW complexes. For now, I just want people to, like, audience to think of them as a set of balls with attaching maps to attach those balls to a CW complex of one lower dimension. You just glue those balls in some way to the lower dimensional skeleton.
So a general 1-dimensional CW complex would be a graph?
Would be a graph. I mean, it depends on how you define graphs, right? You can have cycles.
Yeah, graphs of cycles.
You can have, for example,
sorry, a multigraph.
A multigraph.
Yeah, you can definitely have loops and multiple edges,
Yeah,
as
multiple
this
edges.
example shows.
Yeah. Yeah, so graphs like that. Yeah, I think I
Okay,
will
so
say yes.
so is every one-dimensional CW complex a multigraph? I see. Okay.
I think so. For dimension 1, I think it's that easy, but it can get quite crazy for like starting from dimension 2, I think. Okay. I have 2 more definitions. So can we move on to the definition of regular CW spheres? I'll take that as a yes. So yeah, given a CW sphere, you can have many attaching maps. And by saying a CW sphere is regular, you ask each of those attaching maps to be homeomorphisms. So now look back to this example. Remember how we glue the 2 endpoints of the line segment together to one point to get this equator, this circle over here? That's not a homeomorphism, right? The attached map there was from 2 points to 1 point. So that will make this example a non-regular CW sphere. Okay, but if I add one more vertex here, all of a sudden it's all right. This one with 2 vertices will be a regular one. Okay, and yeah, the last thing is strongly regular. For something to be strongly regular, we just add one more, also kind of natural property that we need on the intersection of faces or cells when you deal with spheres. So basically, we also ask the intersection of any 2 cells, or I'm missing an S here, to also be a cell. And it could be empty. It's okay if 2 cells do not intersect at all, but they couldn't intersect at more than 1 cells. So now look at this current example. Is this strongly regular?
What's a cell?
Think of closed cells as the balls that we're attaching. So there are 2 closed 2-dimensional balls here, right? And what is their intersection?
The union of the 2 line segments.
Exactly, and there are 2 one-dimensional cells there instead of 1. And that will make this example not strongly regular. Okay, and to give the example of a strongly regular sphere, I will add many new vertices. So here is just an example of a nice one, a strongly regular one. Feel free to check that, take any 2 cells, look at the intersection, it's either empty or just 1 smaller dimensional cell. And this, those previous examples look nothing like polytopes. But if you look at this one, you would agree with me that this can be, if I just think of these 2 cells as triangles, because they sort of are, this is very close to a polytope that we saw before, right? It's like a bipyramid over a square. In other words, this one. And that will make this strongly regular CW sphere combinatorially equivalent to this polytope over here, because they will have the same phase pole set. And one might ask if it's always true. Well, you will, okay, a good guess will be no, because I already put this mark over here. But if you try to visualize it, you might want to believe that it sounds about the same. And when you visualize it, you might be right, because you can only visualize up to dimension 3. So in 3 dimension, it's true that if you have a strongly regular CW 2-dimensional sphere, then yeah, it's combinatorially isomorphic to a boundary of a 3-dimensional polytope. Okay, but starting from dimension 4, it's no longer true. And in fact, the difference between these two sets, the set of all polytopes and all strongly regular CW spheres, are very different. The latter is much bigger. And the most famous, I'd like to say that, one of the famous examples that we have is Barnett's sphere. It has d equals 4, so the sphere would be of dimension 3. It has 8 vertices. It's even simplicial, but it cannot be, it's not polytopal. That means it's not a boundary of a 4 polytope. In fact, I think people have a full characterization of all simplicial strongly regular CW3 spheres with exactly n vertices. There are 39 of them, and exactly 2 of them will be non-polytopal. And as D and N go up, yeah, they're just much more, a lot more strongly regular CW spheres than polytopes. Yeah, just too many of them. If you just randomly pick a sphere from that set, yeah, it's almost impossible that the thing you picked is a polytope. And I think that's all I want to include for the pre-seminar. Any questions? I saw someone clapping. You might want to unmute yourself.
I don't really know what context these sort of things are going to be appearing in, but how do you know when something is a sphere? Or do we start with the sphere and like triangulate it or whatever?
Yeah, if you triangulate a sphere, that you will get a simplicial one. But basically, you just decompose. Right? Those are basically decompositions of spheres. And the reason I include that weird strongly regular CW sphere stuff in the very last part is because, first of all, it's a natural generalization of polytopes. And if you have some nice result in polytopes, you might naturally want to ask if it still holds in this more general setting, because they just include more stuff. Or is there a generalization of your theorems in that more general setting? And we're going to see that in the main talk.
Any more questions?
I have one question.
Yeah.
You mentioned polytopal strongly regular CW spheres have the same face poset. So face posets for polytopes are intuitive in the sense of like linear algebra, but like for these CW spheres, what is the explicit relation that tells whether like 2 nodes are connected in the poset?
So I think it's about the same definition. So for the